Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good afternoon to all my students. Hopefully you are in good conditions. Okay, we continue today with our lecture. Still in chapter number 4, second law of thermodynamics, but this is part 3. Okay, first of all, I would like to make the acknowledgements to Dr. Idris Saad, Dr. Al Hassan Salami Tajani, Dr. Nur Afifah Yahya, uh, because of their efforts to produce these slide uh, notes for the students to review. Thank you very much. So I will use this slide together because this slide of thermodynamics is same as our code course MEM 462. Thank you very much, guys. Okay, our class part 3 normally will cover uh, number 5, 6, and 7. That means we will look on the uh, entropy principles, isentropic processes, isentropic efficiencies of steady flow devices such as turbine, compressor and pump, and also nozzle. And at the end of this chapter, we will discuss a little bit on the introductions to the concept of Exergy. So, what you must know uh, in this chapter, actually, uh, firstly, we will look on the meaning of entropy, definitions of entropy, then see the entropy changes, okay, entropy changes that take place during the process of pure substances, incompressible substances, and ideal gases. And also you will know uh, one of the process that's called isentropic process. From there, you will know also the isentropic efficiencies of the various engineering devices. Okay, as mentioned, turbine, compressors, pump, nozzle. Okay, that is what you should able to define, and also you should able to examine it, determine all these analysis um, based on the calculations. Entropy. Okay, entropy, as we learned before this in chapter number 1, sorry, in part 1 and part 2, the second law, that means state that process occur in a certain directions, not in any directions. It often lead to the definitions of new properties called entropy. So entropy is actually is a quantitative measure of disorder for a system. So we can express this entropy as a measure of the unavailability of heat to perform work in a cycle. This related to the second law, since the second law predicts that not all heat provided to a cycle can be transformed into an equal amount of work. Some heat rejections must take place. Okay, that is some of the statement that you have to know and also understand. So the entropy change during the reversible process, we can define as this short formula. So ds, that's mean change of the entropy, S2 minus S1 is equals to integrate delta Q, that's mean heat, over temperature. So this is a formula for the entropy. So if you look on this formula, you know that the entropy is the heat divided by the temperature. That is entropy. So for the reversible adiabatic process, you also know for the adiabatic process where no heat occur or no heat transfer occur, Q is zero. So the changes of entropy is zero. Then entropy at state 2 is equals to entropy at state 1. So the reversible adiabatic process is called an isentropic process. Entropy change and isentropic processes for a process can happen in three categories. First one is pure substances. Number two, incompressible substances. That is liquids and solids. And the third one is ideal gases. So let's me discuss about what happened in the pure substances. The entropy change of the substance can be expressed in terms of other properties, but in general, these relations are too complicated and are not practical to use for hand calculations. Therefore, using a suitable reference state, the entropies of substances are evaluated from measurable properties data following rather involved computationals, and the results are tabulated in the sum manner of the other properties as specific volume, internal energy, and also enthalpy. So when you want to find these entropy values or entropy change, you can use the properties tables given relative to an arbitrary reference state. So as I mentioned earlier in chapter number 2, pure substances, you have been introduced and also been been known how to use the properties table. So in the properties table, it have the symbol of S. Okay, that is entropy. So when we categorize these processes in the pure substances, you can use the properties tables to find entropy change using the symbol else in properties table. So how do you find this entropy change is based on whether the substance or substances is in the phase of mixture or phase of superheated. Okay, that's how you will use. So the formula that can be used is for any processes of change of entropy is S2 minus S1, and for isentropic process, you must know that S at state number 2 is equals to at state number 1. That's for pure substances. Number 2 is for incompressible substances, therefore liquids and solids. So at these situations, for any process that happen in this case, the change of entropy can be calculated based on the formula of C average ln temperature state 2 over T1. And at this situation of isentropic process, the temperature at state 2 is equals to the temperature at state number 1. Liquid and solid can be approximated as incompressible substances since their specific volume remain nearly constant during a process. Through dV, that means the specific volume is equals to 0 for liquid and solid. So the formula for entropy change during the process is determined by integrations, as I mentioned earlier, as you see in the slide, okay, where C average is a average specific heat of a substance over the given temperature interval. You must note that the entropy change of a truly incompressible substance depends on temperature only and is independence of pressure. Okay, that you have to remember. So the temperature of a truly incompressible substance remain constant during the isentropic process. Therefore, the isentropic process of an incompressible substance is also isothermal. This behavior is closely approximated by liquid and solid. So that's why T2 is equals to T1, and this situation is called as a isothermal. For number 3 is case of ideal gases. Okay, for the ideal gases, the entropy change for the process is obtained by integrating the formula, and the formula lastly will become as for the all processes will become as in the box, okay, the red box, left and the right. So in the case of ideal gases, when you want to make the analysis for the ideal gases, you can use these formulas to find the changes of the entropy. Okay, as you see in the formula, it shows that CV, specific heat at constant volume, and also specific heat at constant pressure. Okay, but the difference between this formula is plus and minus. Okay, when you use CP, it will become minus, and you use CV, it will become plus. Okay, for isentropic process, three relationships of temperature, specific volume, and also pressure can be used. Okay, can be used. Okay, these situations is only can be used if the case analysis is in terms of isentropic process, and this process must be in the ideal gas condition. So you can use these three formulas. Okay, ratio of temperature is equal to ratio of specific volume powered by K minus 1. Ratio of temperatures is equals to ratio of pressure powered by K minus 1 over K, and also ratio of pressure is equals to specific ratio of specific volume powered by K. So this is all the relationship that can you use when you want to make the calculations or do the calculation based on the ideal gases for isentropic processes. Okay, that means if the case is the process is isentropic, so you can use this formula. Okay, let's look on the example. Okay, problems. Uh, okay, in these problems, it says that steam at 1 megapascal, 600 Celsius, expands in the turbine to 0.01 megapascal. If the process is isentropic, find the final temperature, the final enthalpy of the steam, and the turbine work. So, firstly, when you want to do this analysis and calculations, you have to know these questions is about what is about this working fluid in this case of questions. So as you see, this question is based on the steam. Okay, that means steam, vapor, and this is not water. This is vapor. So it gives the values, data values. So you just write down what has been given. So from there, you know, okay, uh, it use the turbine. Turbine, the system that uses turbine. So turbine is a open system because it have and inlet and outlet. Okay, so property relationship, you must use a steam tables because steam. So the process that been used here is isentropics. Then the assumptions that you can make here is it is a steady state, steady flow, one entrant, one exit, and also you neglect kinetic energy and also potential energy. Okay, because it not just mentioned in the questions, and also Ke and Pe is too small compared with the other energies. So based on the conservation of mass, uh, the rate of mass at state number 1 is equals to state number 2, and this is equals to m dot. So using the first law of conservation of conservation of energy, you know that this is isentropic process. So this is a adiabatic and reversible. So therefore Q is 0. And then this conservation of energy will becomes as energy in is equal to energy out. So put the equations of energy that based on the conservation of energy. So m dot h is equals to m dot 2h2 plus work out. So since the mass flow rate in and out are equals, solve the solve the work done per unit mass. So you just simplify, restructure this formula. Then W out dot is equals to M dot 1 H1 minus M dot 2 H2. So simplify these equations, and then you will get H1 minus H2. Okay. After you have defined the formula that will be used, then you come to find, okay, using steam tables, because this problem use a vapor or a steam. Okay, that's why it use a steam table. So given P1 T1 1 megapascal 600 Celsius, at that situations you find H1 is equals to 3698.6 kilojoule per kilogram. S1 entropy at state number 1 is 8.0311 kilojoule per kilogram Kelvin. So the process is isentropic. So when it isentropic, that means at state number 2, S1 is equal to S2. So at pressure number 2, 0.01 megapascal, so entropy fluid is 0.6492, determined from the properties tables at pressure 2. From there you will know, and you may make the conclusion that S2 is bigger than SF and smaller than FG. Okay, and smaller than FG. And so what happened is these situations. So this is the saturated region, or this is the mixture region. Okay. So when it is mixture region, at state number 2, you have to find S2 based on the formula. So get the quality, because when it's mixture region or saturation region, so the quality must be fine. So you get X2 is 0.984. From there, getting H2, enthalpy 2 is putting all the values into the equations. Then you will get H2 is 2545.6 kilojoule per kilogram. Since state 2 is in the 2-phase region, then T2 is equals to T saturated at pressure number 2 is 45.81 Celsius. So H1, you know the answer, the value. H2, you know the value. Then put in the equations, and you will get the specific work is 1153 kilojoule per kg. Okay. Okay, that is for determine the turbine work, final entropy, final temperature. Okay, that is how you can get the answer. Okay, so this another questions or problem samples you can try to solve yourself. Okay, discuss with your friends, and then you if you stuck or if you have problem, you can ask me. Okay, this is also for practical problems. Okay, do it yourself in your rooms. Get the answer. Okay, the answer has been given certain cases here, so you can do it yourself. If you don't, you have the problems, ask me in the tutorial. Okay, now we go on the isentropic efficiencies of steady flow devices. Irreversibilities, okay, inherently accompany all actual processes, and that their effect is always to downgrade the performance of the device. Okay, that is the reason. Okay, some the performance of devices will be downgraded because of these irreversibilities. In engineering analysis, it would be very desirable to have some parameters that would enable us to quantify the degree of degradations of energy in these devices. An ideal device would be general adiabatics and have no irreversibilities. Okay, that is in the ideal cases. Okay, ideal. And isentropic devices. The parameter that expresses how efficiently an actual device appropriately and ideals one is called isentropics or adiabatic efficiency. Okay, when you come or when you see the isentropic efficiency or adiabatic efficiency, it means that that is the parameter that express how efficiently an actual device approximately an idealized one. Okay, so so to define the isentropic efficiencies is differently for different devices since each device is set up to perform different tasks. So isentropic efficiency is defined by comparing the actual performance of devices to this performance under isentropic conditions for the same inlet state and exit state. Okay, this is isentropic efficiency of turbine. So this is how you can find, okay, the efficiency of turbine. Okay, turbine, pump, nozzles, all of these devices are we assume as the isentropics or adiabatic process. So as you see here, the isentropic works is the maximum possible work outputs that the adiabatic turbine can produce. Therefore, the actual work is less than the isentropic works. So when you see here in the turbine, it said that the actual work is less than the isentropic work. Okay, so when we talk about the turbine, the straight line, okay, the straight line is the ideal process. The dot line here is the actual process. Okay, actually, if you want to do the measurement of the ideal process, you will get the straight line, the smooth straight line. But in actual case, the performance is not as ideal cases. The performance is in actual case, it have been less than the ideal process. So when you want to find the isentropic efficiency of the turbine, so the formula you need to know for the efficiency turbine is actual process or actual turbine work divided by isentropic turbine work. That means WA actual divided by WS entropy. Okay, isentropy. So to find work actual, H1 minus H2A for the actual. And for isentropic turbine work, H1 minus H2S. Okay, so this is the formula how to find the isentropic efficiency of the turbine. Okay, for the actual process, it is irreversible. Okay, what you have learned last in part 2. Okay, remember when we talk about ideal, it is reversible process. Okay, reversible process. So this is pictures of the isentropic process involve no irreversibilities and serve as the ideal process for adiabatic process. So this is also the diagram of HS diagram for the actual and isentropic processes for an adiabatic turbine. Okay. Okay. Let's look on the isentropic efficiency of compressor and pump. Okay. We skip on the sample problems for isentropic efficiency of turbine. Okay, we go straight to the isentropic efficiency of compressor and pump. So the concept is like the isentropy of turbine, but it is opposite. Okay, it is opposite for the compressor and pump. Okay, for the compressor and pump, to find the efficiency, isentropic efficiency for this compressor and pump, the isentropic compressor work is divided by actual work. Okay, actual compressor work. So the formula will become work isentropic over work actual. Okay, and you use this work ideal over work actual. It will give you the isentropic efficiency of compressor and pump. So to find the efficiency of this compressor and pump, you have to find the work ideals. Work ideal is H to S minus H1 over H to A actual minus H1. And for pump, specific entropy times changes of pressure 2 minus pressure 1 over H2O, H2 actual minus H1. Okay, for isothermal efficiency, the isentropy efficiency for compressor will become work turbine over work actual. Okay, this is for isothermal efficiency. Okay, we skip for the sample problems. Now we go for the isentropy efficiency for the nozzle. Okay, for the nozzle. So isentropic kinetic energy at the nozzle exit is the maximum possible kinetic energy at the nozzle exit. Therefore, the actual kinetic energy at the nozzle exit is less than isentropic value. Since these efficiencies are defined as to be less than 1, so the nozzle isentropic efficiency is defined as actual kinetic energy at nozzle exit over isentropic kinetic energy at nozzle exit. So the formula can be formulated as velocity, okay, velocity powered by 2 actual over velocity powered by 2 ideal. Okay, for steady flow, no work, neglecting potential energies and neglecting the inlet kinetic energy, the conservations of energy for the nozzles will become H1 is equal to H2A plus V2A over 2. Okay, this is only not you don't have to remember this question, but only you have to know how to neglect all the energies that has been mentioned. Okay, based on the conservation of energy. This is as you learn in chapter number 3. Okay, so then the nozzle efficiency can be written as H1 minus H2A based on this equation, this diagram, enthalpy versus entropy. So for the nozzle, this is ideal, and the dot line is a actual process. So H1 minus H2A actual over H1 minus H2A ideal, okay, or isentropic. So this formula you can use to find the isentropic efficiency for nozzles. Let's discuss on this efficiency of nozzle. Okay, it said here air, okay, nozzles that mean use air as a working fluid. So air at 200 kilopascal and 550 kelvins enters an adiabatic nozzle. So it mentioned here adiabatic nozzle. Of course, nozzle you know it is adiabatic, but in this case it assume as is mentioned it is adiabatic nozzle at low velocity. So it said at state number one it's low velocity. We just ignore and is discharged at a pressure of 110 kilopascal. Okay. If the isentropic efficiency of nozzle is 62%, so in this question, it said it have the isentropic efficiency of nozzle 92%. So you have to use the equations of efficiency nozzles. Determine the maximum possible exit velocity. That means it's want to you to find the exit velocity. B, the exit temperature. C, actual exit velocity of the air. So assume constant specific heat at room of air at room temperature. Okay, this is the assumptions. Okay, firstly you have to assume that the situation is steady flow and the kinetic inlet kinetic energy is negligible because it said low velocity for the inlet and air is the ideal gas. Okay, this working fluid is air, so you assume as the ideal gas. So by mean you can use the ideal gas law or ideal gas approach. So the analysis based on the CP K of the air can be taken as 1.099 kilo and 1.354 for K. Okay, this is CP and K. So if you don't know how to remember this number, you can find CP and K for air in the properties table. Okay, the steam table. So A, the exit velocity will be maximum when the nozzle operate at the reversible device. Then for isentropic process, because this is the adiabatic process, so it is called isentropic process. So when it isentropic process, you can use the relationship between temperature, pressure, and volume. Okay. So here, use this one of the relationship ratio of temperature and ratio of pressure. Why I use this? Because this is the only that you have know or you know in the question. So from here, you will get the T uh, at state number 2. Okay, T at state number 2 for isentropics is 748 kelvins. Okay. So from energy balance, you will find the equations will become H2S minus H1. This from energy balance. When you neglect all the kinetic potential energy, and it will become like this. Work and also the heat that have in the equations you neglect, so it will become like this. From here you will find the velocity at state number 2, so then it will give 666 meter per seconds. Okay, because firstly we want you to find exit velocity. Okay. B, the exit temperature. Exit temperature can be found from the equation of efficiencies, isentropic efficiency of this nozzle. So you know the formula of isentropic nozzles is H1 minus H2A for upper is actual divided by ideal. So for enthalpy formula, you can change to Cp delta T. So from here, the temperature, you got the temperature from the equation, question. So T to A will give the answer 764 Kelvin. This is T state number to actual. And for actual exit velocity, using also the isentropy efficiency of nozzle, so from here you will get the answers. V2A is equals to 639. Okay, 639 meter per second. That is the answers for A, B, and C. This is the practical problems. Okay, all the practical problems you can do it yourself as your exercise. So it also have the uh, answer at the end of the sentences. So try to do yourself. If you got problem, ask me in the tutorial. Now let's go to the introductions to the concept of exergy. Before explained what is the definitions, what means by exergy, let's me explain or introduce to you first about the low grade energy and also high grade energy. As you see in the slide, low grade energy, this is the energy that cannot be completely converted into work in a cyclic process. Okay, for example, you can see at the right side of the heat engine. In the thermal energy heat, okay, when the heat at a high uh, temperature, that means from the furnace, cannot be completely converted into work. That means work out here, because some of the heat at high has been rejected to the low temperature resolver.
First, enter your PIN to unlock the device.
Okay. That is a low grade energy. For the high grade energy, this is the energy that can be continuously converted into low grade energy. So, as you see here, for the paddle wheel work, okay, this is for high grade energy, and electrical work, this is for high grade energy. So the thermal energy storage here, heat here, okay, continuously can be converted into a low grade energy. Okay, that is the introductions or the meaning of low grade energy and high grade energy. So let's look on this system on the chart. So low grade energy, intermolecular energy stored in the system by the virtue of its temperature. So continuously conversions through a cyclic process, once to the maximum amount obtained as work, another one goes to the minimum amount left as a low grade energy. So at the maximum amount obtained as a work, it will go or name as the exergy. That means availability, available energy, and work potentials. But in the minimum amount left as a low grade energy, It's named as the energy, okay, unavailability, unable energy. So here is some meaningful figures that you can know about the low grade energy, uh, Exergy, and also energy. Okay, so for the low grade energy, the heat goes to the low grade heat. For Exergy, high grade energy come out from work net, but unavailable energy named as energy is referred to the QL, or heat at low temperature. So this is the definition of energy. It is the useful work potential of a given amount of energy at some specified state, which is also called as availability or available energy. Energy is never destroyed during the process. Okay, that is, it's changed from one form to another, as we know as the first law of thermodynamics. So, in contrast, exergy accounts for the irreversibilities of the process due to increase in entropy. Uh, it as a second law of thermodynamics. Exergy is also destroyed when a process involves a temperature change. So this is the reverse of entropy. So a system is said to be in the state, in the dead state, when it is in the thermodynamic equilibrium with the environment it is in. So death state. Death state actually is a system deliver the maximum possible works as it is undergoes a reversible process from the specified initial states to the state of its environments. Okay, that is called death state. This represent the useful work potentials of the system at the specific state, and it's called exergy. All right. So informations in this slide is about the introduction or the concept of energy. Okay. If you want to understand more, please read the thermodynamics books written by Chengel or McConkie. Okay, for the concept of exergy. Um, that's all for part 3, chapter 4, second law of thermodynamics. Okay, or if you want to understand more, you have to read yourself in the books. Okay, not based on the notes or slide that I have gave. Okay, that's all for this time. Okay, we will see in next chapter. Okay, Assalamualaikum warahmatullahi wabarakatuh.